Yeah, thanks everyone for joining. So Jenny and I will be talking about deep Bayesian bandits, exploring in online personalized recommendations today. So just to set the context of what this is, right? So this is about an online recommender which continuously needs to keep getting updating itself and keeps training continuously based on the more recently seen data and updating the model manager. And then from there, the prediction service will pick up the latest model which has been trained on the freshest data and serve the predictions. And so how do you keep doing this, right? This is called continuous training and prediction. The model used in production to serve data is continuously getting updated, and you are serving from the newer model which is trained on the latest data. So to set this up, this continuous training framework, what they did in this paper was an offline simulation of the continuous training service, and also and for the offline model they retrain it after, and the use case is add clicks. So impressions, and the optimization is to make sure you show the most relevant ad um, to the targeted users. So there's personalization there, and make sure you optimize for click through rate, the users clicking on the ads. And with that business context, they retrain the offline model after every 20 users actions, where a user action can be a click on an ad, or even a dismiss if it's like a negative signal, and eventually you want to like them to monetize on after the click, right, to complete a purchase or something like that. um, and then the online model is updated every 10 minutes in production. So every 20 users who see the ads, the latest 20 users are picked up by the training service, and in the training stream, and the model is retrained, and then the prediction service gets updated with the newly trained model every 10 minutes. So that is the online setting. And then, the introduction of the paper talks about two main toolkits, basically to fix algorithmic bias. So there could be a lot of ways the data can be biased and not represent the actual distribution of data in production. And that's to fix that, typical methods are causal inference, also known as the Bandit theory, and reinforcement learning. And so you want to be able to explore by having a similar kind of distribution. And for in uniform exploration, all items are shown to all users to form an unbiased data set. But oftentimes uniform exploration will not work because most of the, if you show all items to all users, then the multiplication, the cross is too big and the data becomes too sparse, and most of the users are not interested in most of the items. It may not be personalized to them, so they may not click, so the click-through rate will drop. And so because of that, there might be a revenue loss to the business, and there's no information on future expected gain. So there's the other idea from reinforcement learning, which is exploration exploitation trade-off, and that is typically cast as a multi-arm bandit task, where you have an epsilon greedy policy, and then you try to make some actions to maximize the reward and minimize the regret. So that's like been a powerful technique for this domain. But the con of bandit approach is it makes some real world assumptions about the reward environment, and these assumptions cannot be very accurate because the real world is a highly complex setting. And so the paper also explores two uh, algorithms to augment the multi-embedment. This is called upper confidence bound, UCB, and Thompson sampling. So they have some theoretical guarantees, and this is to approximate the posterior distribution. So the actual distribution in production, they try to kind of get some uh, mm, mimic the posterior distributions. The con for these methods is it requires sampling from the posterior distribution, and it can be very computationally challenging. if the value function is approximated by deep neural networks to capture the nonlinearity. And traditional neural networks provides point-wise estimates, but it doesn't have the uncertainty estimate. So you want to make a prediction, the prediction should also give you the uncertainty, saying, hey, this is the prediction, but there is give me a margin of plus or minus 10% for prediction errors, right? So that uncertainty estimating that is very valuable, but traditional neural networks cannot do that. So Bayesian deep learning is a natural solution for that, to fill that gap, but it's also computationally expensive to train and deploy as an online service. So the paper proposes a hybrid model with dropout in the last but one layer. I'll explain a little bit about the architecture later on. And it uses these UCB and Thompson sampling exploration to estimate the confidence interval. So some related work prior on which this paper is built on. For contextual bandits, there are at least these three references given. The UCB assumes, so in one paper, the uniform confidence bound, upper confidence bound assumes linear payoff model, which is evaluated offline with logged events collected randomly. The other paper uses latent class structure. So you have like user embeddings, and then it uses that to train model parameters for each class. But the advantage of that is user features which need not fully capture all the variability, because the embeddings kind of try to map to a latent space. And it creates good recommendations for new users quickly. It solves a cold start problem, and it has a lower regret bound. The other paper is BART, and it jointly optimizes recommendations and associated explanations. So interpretable recommendations for music recommendations, for example. Epsilon Greedy exploration is easier, has a production implementation is slightly easier, and it introduces a concept called propensity scoring. And the other, in the deep reinforcement learning space, something called bootstrap deep Q networks. It adapts Thompson sampling, and it allows temporally extended explorations by approximating the distributions over the Q values via the bootstrap. So, I mean, there is a lot of theory in this, and it's an overloaded sentence. So I probably, if you're interested, you can read up more about DQ and on Wikipedia or something. There are other papers which compare some accuracy of predictive uncertainty under distribution shifts. And then there's also an actor-critic structure to model the long-term rewards. So a lot of times we only capture the short-term interactions, and this one goes into long-term. And how to adapt the user preferences dynamically for the long-term. Deep Page is another paper which jointly optimizes a page of items with the real-time user feedback. Yeah, so with this, the paper's approach, I think, Jenny, you wanted to take over from here?
Yeah, would you mind letting me share my screen so I can have better control?
Yeah, sure.
Okay, so you can see my slides, right?
Yep.
Okay, excellent. Right, for this paper, the approach is just frame this problem as a contextual bandit, and the context contains both the user and the ad features, and the neural networks that they use will take this context and predict the click-through rate for each of these ads served to a different user. So to help determine whether we want to just pick the best ad that we think would generate the most click-through rate versus to explore, serve the users with random ads and see how the user reacts, we need to use some sort of exploration algorithm. So some sort of algorithm that tells us which ad to serve the user based on model output, or both based on whether we want to explore different types of ads with these users or not. Many of the exploration algorithm that the paper uses requires sampling from the posterior distribution of the click-through rates. So the paper also needs to somehow approximate this posterior distribution of the click-through rates before it can use some of the exploration algorithm from the paper. So of course, the next step would be to, after you serve the user with certain ads, you watch their action, and then you log that for future fine-tuning of your neural network. So the paper uses basically two different neural network architecture, and Suha might touch on this a little bit later as well. They have an offline experiment. The offline experiment is presented, the experiment is done on a public data set that has that basically served 300 different ads to 120 different users, and the users each rate how likely they are to click on these ads. So a very nice full user ad interaction matrix, which you usually won't get in the real world, but it's a nice experiment to compare your online results to. And then there is the online experiment, which is done on Twitter ads. So a lot of these paper co-authors are from Twitter, so they do their experiments on Twitter. And there is an online and offline evaluation as well. And I'm sure Suha will go into that a little more later. For the offline experiment, they use a fully connected feed-forward neural network. And for the online experiment, they use a modified version of the wide and deep neural network. So original wide and deep network is shown on the left. Their modified version is shown on the right, where they insert an extra layer to the second to last layer. And we'll get into that in a little bit. So there are three different exploration techniques that this paper uses. One is called the Epsilon Greedy. So for Epsilon Greedy, the idea is that your model produces what ad they think the user is going to click the most. Epsilon Greedy is going to select the best action most of the time. So you can generate a random number, and if the random number is larger than epsilon, then you'll choose the best output from the model. If it's less than epsilon, then you'll just randomly choose some ads. So you can explore how the user is going to interact with these randomly chosen ads. And epsilon is usually set to a small number, like maybe 0.1. So you're only randomly choosing things 10% of the time. Most of the time, you're choosing the best output from your model. Another technique is Thompson sampling. So for Thompson sampling, you need some sort of posterior distribution. So after training your model for a while, you have a posterior distribution of what you think your click-through rates would be. And you sample from each of the posterior distribution of each of the items once, and then you pick the sample that has the highest click-through rate. So this is not from the paper, but this is just for illustration. So for example, if you have 3 different ads and each of them has a posterior click-through rate distribution, you just sample one from each of these ads and you pick the ad that has the highest sample click-through rate. And over time, you should be able to find the best ad to serve to your user. And the third exploration technique is the upper confidence bound. Each of the ads have some sort of mean click-through rate, but you don't know what the mean click-through rate is. But you can theoretically establish an upper bound for each of these ads click-through rate so that you are confident to a certain level that the mean click-through rate for each of these ads is below your upper bound. And you use that upper bound to choose the ad with the best click-through rate. So the idea is over time, these upper bounds is going to converge to more or less the true mean of your ad click-through rates. So if you select an ad with an upper bound that's a little too high, then you won't get a click and you will revise the upper bound a little bit lower. So we have the 3 different exploration techniques, and the Thompson sampling and the upper confidence bounds, at least the way the paper does the upper confidence bounds, both require sampling from the posterior distribution. So then the next problem is, how do you approximate a posterior distribution? Neural network, traditional neural network output is not going to give you any uncertainty or any distribution. So how do you approximate this distribution? How do you introduce some uncertainty into your model output? So there are several different ways the paper approached this. They tested a bunch of different methods. One of them is bootstrapping. And there are several variants to bootstrapping. One is the original bootstrapping, where you get your uncertainty by training identical models on different subsets of data. And then there's a variant that uses a multi-head neural network to do the bootstrapping. And you can also train multiple networks on the same whole data set and rely on stochastic gradient descent and also the random initializations to introduce the uncertainties. And then there is a multi-head network variation of that as well. So these are the original bootstrapping is called bootstrap. The multi-head neural network, they call it multi-head. The third version is called SGD, relies on SGD to introduce uncertainty. And then there is the multi-head SGD. So you'll see these abbreviation in the tables later. This is what they're referring to. Another method to approximate a posterior distribution is just use the dropout method. So you train a network and you make predictions through multiple forward passes with different dropout units, and the different dropout units will give you slightly different results each time. And there you can have a distribution of the click-through rates. So the pros for the dropout method is that it has lower computational costs compared to bootstrapping, but the con is that it tends to take longer, and I believe the paper says 2 to 3 times longer to train a neural network with dropouts. And also just doing this multiple forward passes with different dropout units can still be expensive. So what the paper does is it produces it suggests a hybrid method, which is took the original wide and deep model, and it adds a dropout layer as the second to last layer. And the only dropout you apply to is the second to last layer. The rest you don't have to do any dropouts. So you're only computing the bottom layer once, and you're only doing the dropout on the second to last. So that helps speed things up a lot compared to the original dropout method. So through this, you can get a fairly decent posterior approximation algorithm, and then posterior approximation, sorry. And then you can use that posterior approximation to do your Thompson sampling, or you can do your UCB. So for this paper, the way they estimate their upper confidence bound is through a cumulative distribution, is making use of cumulative distribution functions. So what it does, for example, when you want to estimate the upper confidence bounds, is you use this dropout layer to do the computation 100 times. So each time you have different dropout units, so you get 100 different values. And then out of these 100 different values, this paper will take the 5th largest value and say that we're confident that the true mean of the click-through rate distribution is less than this 5th largest value to a certain confidence level. So using the upper confidence bounds, you can decide whether which ad you want to give to your user. So that's the paper's approach, several different posterior approximation algorithm and several different exploration techniques. And they tested many of them on their online and offline experiment. So here I'll hand it back to Suha for the experiment and their results.
Thanks, Jenny. So here, oftentimes in the real world, when you show an ad impression to some user, you don't get an engagement in terms of a click immediately. So there's a delay. They may not even click on it in the same session, but if you keep showing them again and again, maybe sometime later, like a day or a few hours later, you may get a click. And so how do you model the correct distribution, right? If you're training continuously, you have to account for that delay. Um, and so the distribution of the time to click delay, it kind of looks like this. So if this is on the x-axis is the time to click an impression, right, in minutes. So most of the people click immediately, but then there's a long tail distribution of people clicking even like 2-3 hours after it's shown. And so given this kind of a distribution in the real world, if you kind of wait out for a few hours, then I think you should be able to gather most of that the effects, and then based on that, you have to build in that latency into your pipeline. So we already spoke a little bit about this, the neural network architecture. And for the loss function, one thing they do mention is fake negatives, right? So this is the thing that if a user has not yet clicked on something, they treat it as a negative, but then a day later, if they click it with a delay, it's considered as a false negative, but then which actually was a positive because it was clicked later on in time. And so the way they model that behavior is to replicate that data point and duplicate it to a positive label. So as to model that delay. And then it's ingested into the training pipeline after the delayed user engagement. So for the experiment setup, right, for the offline simulation, they use a data set called AD16, public data set, and it has a full user ad interaction matrix with the ratings of from 1 to 5. For 1 is they didn't interact at all, or even it was a dismissed ad, and 5 is a really positive interaction. And 300 ads were also shown to 120 users. This is a second kind of simulation, not just on the public data set, but they also showed 300 ads to 120 users, and it has 250 user features and 323 ads features. And the categorical features are one hot encoded, and for each user, they hold out 5 ads as the test set. And some of the metrics are sum of the average click-through rate as the reward function, and area under the precision recall curve as one of the metrics. Um, and here they only optimize for the reward, but not for the regret. So not minimizing for the regret is also typical for bandit models. And they give a list of the hyperparameters they use here below. So the model selects 7 different ads, and RMS propagation optimizer with a learning rate of 0.1, decay rate of 0.5, batch size of 64, 100 training epochs, and dropout of 0.5, which is half the cells outputs are dropped. And 0.1 is for the epsilon in Epsilon Greedy, and number of samples for the upper confidence bound is a formula number of bootstrap networks divided by heads, and the value here is 10. 90% is used as the confidence threshold, and second largest value of 10 samples are used. And then for the offline model evaluation, right? So they train on 1 day of data with 500 million ads and test for 1 hour the next day on approximately 20 million ads. And online, they do a random policy for randomly sampling unbiased 1% of production traffic, approximately 160,000 ads. They use a metric called relative cross entropy for the online, which measures the improvement over the naive cross entropy. And then the hyperparameters here are listed here as well. And some of the results. So here, so there is so some things to notice, right? This is the random sampling. There is no click-through rate at all. Everything else is that's like the considered as the baseline, and others are measured on top of the baseline, the gains. There's a trade-off here between the click-through rate and the precision recall AUC curves, right? So as you optimize more and more for the click-through rate, you are becoming more and more selective for a particular user, so your coverage may drops. So as in, if you don't find any ad relevant to a particular user, you may not show anything to them at all, so no ads. So in that sense, the recall drops. And then the precision also, if you want to optimize, you have to have a high precision, but recall is then becomes so low that overall PR AUC curve kind of drops. So you'll see an inverse correlation between the click-through rate column and the PR AUC. So the highest PR AUC here, 0.65, is 91.7 click-through rate percentage improvement, which is lesser than the 139% here. And for the 139, have only 0.53 of the AUPR. So that is one observation. And the next observation, UCB earns more rewards than the Thompson sampling. So if you compare just the UCB lines with the corresponding Thompson sampling, right, UCB will be higher on the click-through rate here too. Um, and so basically, the highest reward bootstrap UCB has the highest computational cost, but also the highest reward. So that is that you're trading off more computation cost for higher performance here. And if you see the hybrid model right at the bottom, it has a pretty low click-through rate, but it has a the hybrid with Thompson sampling has a pretty good PR curve. But then it tries to reduce the computational cost by introducing dropout, and the effect of that is, since you're dropping out a few output layers from a few nodes of cells, your model takes 2 to 3 times longer to train, and your click-through rate also drops. And then the currently used in production for them is the greedy method, greedy policy. And if they had to swap that out to a different method, they do have the comparison against that as well. And then this shows the number of epochs you train for the hybrid model, 100, 200, 500, and how that affects the training PRAC and the click-through rate in the test one. So the model can be warm started offline with longer training epochs before deployment. So hybrid model can run offline, and then that can kind of overcome the cold start problem. And serving more ads, right? The increasing the recall might not linearly result in revenue gain. So if you have a high, if you want to optimize for high test PR AUC, that means your recall is going to be high. You're probably serving irrelevant ads to users, so you cannot expect them to click on it. And so what really matters to improve click-through rate is the precision and not as much the recall. And then the Epsilon Greedy approach here in A/B testing, they did an A/B test with the Greedy versus the Epsilon Greedy. It resulted in 100% increase in the negative engagement. So that is, users didn't like the ads at all and they dismissed it. And the reason again is because of the high test ARPUC of 0.66. That means probably recall is high, you're showing irrelevant ads, and so that caused a lot of dissatisfaction to the users. But compared to that, the hybrid model, it did not have any negative engagement, and due to the use of upper confidence bound, which shows ads that are consistent with users' preferences. So those are the main takeaways from the paper. And yeah, any questions, we can take them, or we are also at time.